Okay, we studied about continuous version of RC circuit and their impersistence and their meanings. We study about that. At this moment, I would like to convert the continuous RC circuit into a discrete version of the RC circuit. So discrete version RC circuit can be developed from the continuous version of RC circuit. So I do like to rewrite here that the continuous version RC circuit first. Continuous version RC circuit dv or t of dt r equals to vi over what is this? Okay, I think this one should be deleted, and I would like to write down. Okay, dvo t over dt plus equals to vi t over tau minus vo t over tau. This is the continuous version RC circuit. Okay, this is the continuous version RC circuit. I would like to make it discretize. To discretize it, this is time axis, and output signal patterns are given like this way. For example, this one is output t. Then I can sample it like so okay, this one is t equals 0. So this one is v o 0. Next sample are taken at ts, and the output will be vo ts. And the next sample are taken 2 times ts. This one is a vo 2 ts. Goes on, and a certain n times ts. The output will be vo n times ts. Okay, this is sampling process. I can add up negative times at here, minus ts. Okay, then this one is vo minus ts, and minus 2 ts is also possible. Okay, this is all the way goes like that. Then we can converting this one into a sequence. It means that the 0 is 0, 1 ts is 1, 2 ts is 2, and like this sequence, nth sample as n, and minus 1, and this is minus 2. And similarly, vo0, okay, this is 0. The vo0 can be given vo0 sequence, and vots is vo1. Okay, this is 2 ts. Okay, then this output is vo2, like that, and nth output is vo n. Minus 1 is vo minus 1. In a sequence domain, we can understand in this way. Okay, it all goes all the way this way. So sampling process looks like this one. There is a continuous version of output VTI exists here, but we take a sample at every ts times. Okay, this one it should be 0. So this is time difference is ts. Okay, then we would like to convert that equation into a discrete version. To figure out the discrete time version, I would like to convert the rate of change is looks like this one, delta VO over delta T. So this one is derivative terms like that. Then we can write down here that time difference is always TS. So that's the TS difference in discrete version. So this is TS. And the voltage difference is sample to sample difference. So VO n plus 1 sample minus VO nth sample. This is delta V. Equals to tau over V I n. Input also sampled at every TS second. And minus V O over n tau. So this equation is a discrete version of continuous time sequence. Okay, so I would like to rewrite this one into by multiplying TS and pushing VO to the end to the right hand side. Then VO n plus 1 equals to okay, TS is multiplied over here and this is shifted back, so I can write that one minus TS over tau and times VO n and minus TS over tau. See that? VI over n. Okay. So this can be expressed into a alpha. Okay. I rewrite the difference equation into this way. VO can be VO replaced by output, since this one is output side, so I would like to replace VO into a Y. Okay, then Y O n plus 1 n plus 1, okay, equals to alpha. See that? VO n plus, okay, this should be positive, sorry, beta times VI, okay, VO is replaced by Y and VI, okay, VI replaced with X, okay, then this gives the X over N, and alpha equals 1 minus TS of tau, so this can be written like this here, tau minus TS, okay, and alpha beta equals TS over tau, and you need to know that the alpha plus beta equals to 1. Okay. Okay, alpha is this one and beta is this one. By adding alpha plus beta, satisfy these conditions, and the output sequence are given like that. So we converted the continuous RC differential equation into a discrete difference equation, okay, by similarity. And from here we can choose arbitrary value of TS, and from here and also that the tau is a resistor times capacitor. This is time unit. This is tau, and the TS is sampling period. We can choose any time steps, but from here I just take TS time step as 10% of tau. We can choose any kind of time step, but if I choose this one, then alpha will be if this is 0.1, so this is 0.9 becomes 0.9, and the beta will becomes 0.1. Then we can rewrite, okay, yo is not yo, this should be y. Okay, we replaced vo with y. Then I can rewrite the discrete time version system equations like this one. And plus 1 equals 0.9 yn plus 0.1 xn. Okay, we got the equations. But our main concern is to find out unit step and impulse response. It means that we would like to find out the system response of this discrete system. This one is discrete time system. We would like to know when we applied unit step sequence is applied to the input, then what will be the output sequence. Then this is step response. Impulse response can be, think about this one. If we applied unit impulse sequence is applied, then output will be this one. So conventionally, when we apply the impulse, that the impulse response output usually take a H symbol to show that the impulse response. As we have done here, I said that the HT is impulse response of the continuous domain. But discrete domain also the same. If we apply the delta to the discrete time system, then the output is represented by the HN sequence. So we would like to figure out the step response and the impulse response. It means that if we take xn, okay, this one, x n, xn with unit step, then yn is a step response. And similarly, if we choose an input sequence as a unit impulse, then the output sequence is called impulse response. But the impulse response, usually we are taking symbol as H. So output, we are using the H symbol. So we would like to find out the step and the impulse response from these systems. The unit step is a little complex because of the property of delta, the unit step sequence. But the delta is a very simple equations. You know that the unit impulse sequence delta n are defined. It is 0 if n equal 1, n equal 0. Sorry, and all the other cases it's 0. Otherwise, it's 0. Okay, this one should be sorry. It's okay. So delta sequence, unit impulse sequence are defined. If n equals 0, it is 1. All the other cases is 0. So we would like to calculate the system response. We know that the event occurred at the n equals 0, but n is less than 0, or the y is 0. So from these conditions, y n equals 0 if n is less than 0. Okay. So what about we are taking 0 at these conditions, y0 cases. Okay. Then we would like to measure y1 first. y0 we assume that the 0, and okay, n equals 0. n equals 0. if n equals 0, this becomes y1. In this case, y0 is 0. Okay, we know that from here, y0 at 0. So this is 0. So this one is unit impulse. Okay, because of that, this is 0.1. And the next n equal 1, then y2 now this one is a unit impulse. If n is n equal 1, this goes to the 0. So only 0.9 is remain. So this case is 0.1 times 0.9. So n equal 2. Then y3 equals to 0.1 times 0.9 to the square. So we can do this one all the way down. So in case of n, it gives a yn plus 1. Okay, let's try that. Yn will be 0.1 times 0.9 to the 3 cases is 2, so it is n minus 1. Okay, this is the general terms for the impulse response. So I would like to replace this one as h. So in case of impulse is applied, the output sequence usually expressed by the h sequence. So this is the impulse response. Hn is 0.1 times 0.9 to the n minus 1. Okay, this is also h. And this one also h. Input is applied unit impulse, so that we calculate the impulse response of this discrete time version of the system. So if you plot the response, it looks like this one. This is sequence n. If n equal 0, then this is 0.1. N equal 0 is 0. Oh, sorry. N equal 0 is 0. N equal minus 1 is also 0. So all the way down is 0. But n equal 1 is 0.1. This is n equal 1 case. N equal 2 is a scale down, like this one. It's 0.1 times 0.9, 90% of the first term. The third term also decayed, like that. It's a decay. In this way, it's a decreasing. This sequence is Hn. So the memory patterns are shown here. This one is the impulse response. So if we know that the impulse response, by use of the relationship between impulse to the unit step, we can find out the stem response. We know that this equation is a linear and time invariant. So we can using the linearity and the time invariance property to deriving the result of that one. So to calculate the stem response, we refer to the relationship between delta and unit step sequence. Unit step is defined by some m equals to minus infinity, taking sum of delta m equals to unit step. So this is the relationship between the unit impulse to the unit step. Okay, we would like to figure out the stem response. We know that the impulse is applied, we get the impulse response. But what if we apply the unit step? Then what will be the output response? So output will be yn. Unit stem response will also similar relationships. This one is up to the n, and we are taking. Actually, we can take it from 0 because all the other terms are 0. So we can choose from one, you know that H M. We can actually, we have to summation from minus infinity to the n, minus infinity to the n, to preserve the relationship for the delta to the un given by this equation. So we have the summation from minus infinity to the n for the hn, but the hn is 0 all the way 0 if it is less than 1. So we can choose from this relationship. There's no such a difference. Okay, so we can sum up these terms. We know that this one is a power series. In case of power series, we can sum up easily by use of the product factor. That's the 0.9. So it will give 1 minus 0.9. The common ratio is 0.9. Okay, and the first term is 0.0 or 0.1 minus the common ratio is 0.9, and the number of term is this one is n minus 1. We have to one more factor should be added here, so the shows like this one. Okay, then we can figure out that it is 1 minus okay, I'm sorry, this one is omitted. 0.1 times 0.9 n to the n minus 1, so this one should be 0.1 times 0.9 to the n. Okay, this is it. So this will give a 0.9 to the n. Okay, this is the unit step response compared to the unit step response for the continuous version. Here, continuous version unit step response. Okay, I would like to rewrite that one over here. In case of unit step response in continuous domain, continuous system, it looks like this one. Okay, I think changed line. Okay, more lines. Minus t of tau. So I would like to discretize. Then we owe n times ts are given like this one: 1 minus exponential minus n times ts over tau. So we can write down this into this way: e to the minus ts over tau to the n. Okay, we can rewrite this one. Compare these two things. We choose this one as 0.1. Then that's quite similar to this one. It means that if I calculate this value about 0.1. Okay, is this working? It didn't calculate that one, so I have to use Excel. So I mean that exponential minus 0.1 is similar to 0.9. Okay, you can see it's almost equals to 0.9. So we can approximate this one into this way: 0.9 to the n. Okay, we can approximate continuous version with these equations like that. Compare unit step response in discrete time version and the continuous version. And so this continuous version sampled every ts seconds, n times ts seconds. Then it's quite similar, but not exactly the same because of these approximations. Okay, so anyway, we try to convert the continuous version RC circuit into discrete version RC circuit, and build up the system equation from here, and test it firstly impulse response. So we got the impulse response Hn. And from the relationship between impulse to the unit stem response, we can derive the unit stem response from the impulse response. Okay, we figure out the impulse and stem response from these system equations. And the last topic that I would like to mention is convolutional relationships. To understand the convolution operation, I would like to plot a input sequence, something like this one. This one is the input sequence. Okay, and I would like to measure the output sequence at time sequence number n, yn. Would like to find out. Okay, so to find out this one, I want the output contribution at the mth input sequence. Mth input sequence is this one. This one will affecting in somehow to the output. This pattern contribution weighting factor are given by the impulse response, because you know that this system is derived by the RC circuit. So this one is obviously linear and time invariant. If a system is linear and time invariant, then we can apply the linear time invariant system response. Okay, here are a system. Then we applied delta n, then output will be Hn. So this was the impulse response. But now we applied a input sequence like this one. You know that if we multiplied xn times delta n minus m, then this one looks like xn times delta n minus m. So at this moment we applied this sequence. Delta function is scaled and shifted. Okay, scale means that in the linear systems output is just scaled this much. Okay, times, and you know that delta function is shifted to the m. Then because this one is a time invariant, output sequence are shifted the same amount of time. So this should be the output. So we would like to think about this terms. What does this means? This one is xm, and this one is scaled this much. The scale factor of this one is, you know that this is the separation from the current time and the previous data. So that difference is a scale factor. But there are a lot of different inputs that exist here. So we need to sum up all the effect. So we need to take the sum in somehow these terms. So we can write down the output sequence like this way. Yn. Okay, let's think about. Now write down the output sequence. Yn equals, Yn is this one. We need to sum up all the contribution to figure out the output. So previous all the data. So we have to sum with respect to m, x m c dot h n minus m. We need to sum up this one. But think about what is possible m value. M should taking all these value up to minus infinity, starting from n to the minus infinity. So the summation range are given into this way, infinity to the n. Okay. If the system, you know what, this system is the causal system. The previous, you know that the future data cannot affecting the current data value. So we can taking this value up to infinity. It doesn't matter, but we can using this convolutional equation. It's also okay. You know that the m taking only past value, current to the past value, not the future value. So m can taking from n to the minus infinity. Okay, so this is the convolutional equations. You can safely choose this n as infinity in case of causal system. You know that. Non-causal cases, we can extend it one also, because if the future data affecting the current, we have to extend this value. But at this moment, this one is a causal system, so we only consider all the way down to the past and the current value. So we can replace this the variable n minus n with a k value. I mean that the k is replaced n minus m, and from here m change from minus infinity to n. Then k will changing from, if you replace minus infinity over here, that will give infinity, and if you're taking n, m take n, k goes to the 0, so go to 0. So the same output yn can be replaced by some m of you know that if I take a k as n minus m, m can be given n minus k. Okay, so x n minus k, okay, times h k, and m changing from 0 to the infinity. Just a change of variable. Okay, by change of variable, the same sequence can be expressed in this way. You know what I mean, that this one is the same as this should be k, sorry, this is k, m x m, see that, h n minus m, and m is taking minus infinity to the n. So these two equations are the same things. We call this is the convolutional operation. So xm is the input value, h n minus m is scale factor. It's the same. If we think about n minus k terms, that scale factor is hk, because xn is a separated k indexes from the current point. So this is the convolutional operation. Okay. Similar to continuous version, we talk about continuous version convolution operation from here. You can see we can express the input is scaled by the impulse response. So we can understand the convolution operation is past history weighted sum. Weighted sum over past history is the convolution operation. It's the same thing can be applied here. So past history of the input is weighted and sum over weighted past history is the convolutional operation. So at this moment, I would like to calculate the unit step response. In case of unit step, I mean that the input xn xm equals to unit step. Then we know that the unit step response output. So if xm is a unit step, then what will happen? So the step response can be calculated from the convolution operation. So this one can be sum m over xm h n minus m, and minus infinity to the n. Okay. Think about it that the m is less than 0, all terms are 0. So we can safely remove this one as 0. And if m is positive, this one is 1. So we can replace that equation into this way. And the same thing can be applied these equations. Sum k x n minus k, and this is that hk, and k can taking value from 0 to the n infinity. So think about this one. At this moment, x is unit impulse. So if k is n, it's a 0. So that has value. If k is greater than n, it's 0. If you know that n is larger than n, then the index number is negative, then unit step case is 0. So we can think about that we can up to only n is possible. Okay. If k is n, k changing from 0 to the n, if k replaced by n, it goes to the 0. K should be less than n minus. It means that the xn to be 1, this unit, the index n minus k should be positive. Okay, so k less than n. So that is applied here. So in that case, we can assume that the unit step case, this is 1. So this is 1. So both of this sum is the same. By taking sum, as we have done here, so because the h0 is 0, so it doesn't matter the 0 terms. It says the same result that comes out here. So and here we talk about the convolution operation. We know that the system is has some impulse response hn. When it means that if we apply the impulse sequence at the input, then output comes out hn. In that case, arbitrary input signal is applied, and would like to measure output response at yn, at this n. Consider the m's position xm. To figure out that one, we sampled it by use of delta function n minus m. Because n has value only at m, so we can replace this one as this way. So in that case, this one is the delta input, delta n, and this one is just the scale factor. But this system is linear, so the output is just the scaling this much xm. And the time invariant, so input shifted version, the output is just shifted. So due to this xm input, output will be xm times hn minus m scale factor, but m can take in all the past history. So to figure out the output, we have to sum up all the history. So the equation can be given like this way. This equation is called convolutional. So convolution operation is weight the sum of the past history. Okay, we weight the sum of weighted past history. That's this convolution operations. So we prove the property we try to calculate by use of convolution operation for the unit step input. So unit step input applied. This unit step is 1 for a specific summation period. So you can see that both of these two summation shows the same result. It will give 1 minus 0.9 to the n.